Good afternoon, everyone. So hopefully everybody can hear okay. We're in a different room this month than we were previous times. But today we have, as part of our lab here, by the way, I should start off, I never do this. My name is Rory Roberts. I'm a professor of mechanical engineering here at Tennessee Tech as part of the Propulsion, Power, and Thermal Systems Laboratory. And as part of this, if you haven't been able to attend one of these before, as part of this lab, we have the students and researchers do monthly webinars, and this is one of them. And as you came in and logged in and went on the link to the website, you would probably see previous archive talks, for those were our YouTubes of the previous presentations we had. And so feel free to please go and check those out. But today we have PhD student Alex Tharpe, who has been with the lab for, I think this is your second year? Yeah. He was an undergraduate for a year or so doing research, but today we have Alex with his, he's been working for about a year learning CFD, learning reaction flows, and a bunch of things I don't think he imagined he'd be learning in a year. To present his work as part of our NASA ULI, which is the Carbonless Electric Aviation, called CLEAN project. And that's where we're using ammonia as the primary zero carbon fuel. And so as part of that, we started to really look into what is the impact of ammonia and actually probably some hydrogen combustion, and how do we mitigate NOx, because that's a big concern in trying to drive zero emission. So Alex will be presenting for around maybe 25-30 minutes, and then we'll have questions after that. So please just kind of hold your questions till then. But thank you all for attending and for your support. So with that, I'll hand it over to Alex.
All right. Thank you, Dr. Roberts, and good morning, everybody, and thank you for coming in today. Once again, my name is Alex Tharpe. I am a PhD student working on the NASA CLEAN project, and I will be giving a presentation called An Exploration of Ammonia NOx Emissions Using CFD. So in the NASA CLEAN project, we are developing a concept for a gas turbine engine to be retrofitted onto a Boeing 737 that is powered simultaneously by solid oxide fuel cells and a normal gas turbine combustor. And these solid oxide fuel cells require hydrogen fuel to operate, to do the electrochemistry within its walls. So you would think that would mean you would need a hydrogen tank on your aircraft to do the electrochemistry. Well, we found working on this project that using pure hydrogen is more trouble than it's worth. Number one, pure hydrogen, being as small of a molecule as it is, requires special materials to make the tank out of to perfectly seal it. And also, because hydrogen has a very low volumetric energy density, you need a bigger tank to be able to store the total amount of fuel you need to fly from point A to point B. That hurts your mass and weight budget, and also the economics are kind of damaged a little bit. So instead, we're wanting to use pure ammonia fuel. And the reason why we can use pure ammonia over pure hydrogen is because ammonia has hydrogen in its molecular structure. And you can crack the ammonia before it reaches the fuel cells, and you have your hydrogen fuel for the electrochemistry. And there's some other benefits using ammonia, such as that there's a well-established global infrastructure. It's a little bit cheaper and easier to get a hold of ammonia fuel than it is hydrogen fuel. And because the volumetric energy density of ammonia is a little bit higher, you don't need as big of a storage tank on your aircraft to fly the same distance. So that's great. Ammonia does not have carbon in it, so it's carbon free. So it's quote unquote green compared to kerosene or Jet A, and the other hydrocarbon fuels. But it's not really that simple. Ammonia has a big problem in that it is notorious for NOx emissions when you burn it. And this is because of the additional nitrogen in its molecular structure that it adds to the system that other hydrocarbons don't have. And so what is NOx? NOx is a family of nitrous oxide gases, and ammonia outputs a mole fraction of NOx emissions of about 2,000 parts per million at a 0.9 equivalence ratio, which is slightly RIT, which is almost stoichiometric. And there's a weird thing where if you were to do, what I read in papers, that if you do equilibrium calculations, of ammonia combustion and its reactions compared to other hydrocarbons, you should technically get more NOx with the other hydrocarbons if you go off like the flame temperature differences. But the problem is that in the real world, most chemical reactions don't reach chemical equilibrium, where the before reaction rate equals the back reaction rate, so nothing changes too much in the differences in the composition. Well, the issue is, well, because in the real world, that's not how that actually works normally. Ammonia beats out the other fuels that should theoretically emit more NOx because of the imperfect combustion in the real world. So, and a couple more things about the NOx gases. There's two main particles of NOx that need to be made aware of. The first one is nitric oxide, or NO. This particle is the most prominent, most abundant out of all the other NOx emissions. And this particle is very bad because it is actually a huge component of acid rain and smog in big cities. Matter of fact, nitric oxide is the reason why smog has that dirty gray-brown look that's associated with it, and a bunch of bad health effects and all that when you breathe it in. And the secondary particulate of note is nitrous oxide, N2O. And this is also gained a lot of attention because when you compare it to CO2 in its strength, in its ability to hold in heat from the sun as a greenhouse gas, it's roughly 300 times more potent as a greenhouse gas than CO2. So the conclusion that can be made is that if all the power systems in the world that rely on that use hydrocarbon fuels were to switch over to ammonia combustion-based processes without addressing the NOx emissions, we would arguably making the pollutant situation worse with ammonia than we have been with CO2. And before you can work on finding ways to counteract these NOx emissions, you need to understand how they work first, like what mechanism actually forms NOx. And there's three main ones. There's thermal, prompt, and fuel NOx, and we'll go over each of them. So thermal NOx is NOx that forms by the oxidation of the ambient nitrogen in the air through sheer temperature alone. And this phenomena is shown in the Zeldovich mechanism at the bottom of the screen, where if you plug in temperature into the equations down there, you will get the rate constants for each of the elementary steps that forms NOx. And when you plug in a low temperature, you get low to even zero NOx. So if you plug in 300 into the temperature, you'll get a very small decimal number. But if you go above a certain temperature, which according to this chart is about the 1300 C mark, that number changes depending on who you ask by 100 degrees or so. The NOx formation ends up skyrocketing exponentially. And the reason why there's a delay is because the ambient nitrogen in the air has a very strong triple bond that binds it together. Think of it as like the nitrogen atoms are chained together with 3 padlocks. It takes a lot of work to break those locks. And so when you get to 1300 C, now the nitrogen has the energy it needs to break apart, and you keep ratcheting up past that, it cascades out of control. So in normal gas turbine combustors, you can deal with thermal NOx by having really lean combustion where the flame temperatures are really low, or you dilute the flame with colder secondary air to quench it. And if I hadn't said it earlier, this is the most prominent path of NOx formation. Every fuel deals with thermal NOx. Prompt NOx is a bit of a weird one. This NOx is a result of direct combustion reactions in the flame zone. So the difference between prompt NOx and thermal NOx is that thermal NOx can be generated outside of the flame just by how hot the inside of that chamber is. Whereas with prompt NOx, in the actual edge of the flame itself, you have reactions that lead to the formation of NOx. And if you see this diagram in the top right of the screen, this reaction network, if you start with N2, and this is using a hydrocarbon fuel. I don't remember which fuel it was specifically, but most hydrocarbons follow this chain. You'll see you can see stuff like NCN, CN, HCN. Those are not NOx particles per se, but they are precursors. And you follow the chain, and eventually you lead to NO or N2O. And prompt NOx is I don't know per se if it's universal to every combustion, and I don't know if carbon is a must-have for a NOx to be considered prompt NOx, but either way, because this path of NOx is the least influential, you generate a negligible amount of NOx. There's no real need to try to control it, because you can't. It's inherent to the combustion reaction. And then finally, the most importantly, is fuel NOx. And fuel NOx is NOx that's generated as a consequence of additional nitrogen being added to the system. And this is why ammonia is so notorious for its NOx emissions. So most other hydrocarbons do not have nitrogen in their structure. So all the NOx that they emit is due to either thermal or prompt. And the reason why ammonia is different, because again, it has that single nitrogen in its structure. And when you burn ammonia, the bonds that bind nitrogen and hydrogen together are not as strong. They will degrade over time. The hydrogen will break off to form water or other radicals. The nitrogen will either form other radicals of N and H, or sometimes they can even break off altogether to where they're isolated and they're free floating. So because those lone nitrogens are not bonded to anything, they're more probable to bond with oxygen to generate NOx. So thermal and fuel NOx can work together to really exacerbate your NOx emissions. Matter of fact, this is why coal is oftentimes a really bad NOx emitter too, because coal has the same problem where it has nitrogen in its molecular structure. And there's a couple things you can do. There's only one real way to deal with fuel NOx, and that is to separate out the nitrogen. And at least with ammonia, you can preheat the ammonia to where you crack it into N2 and H2. And there's a bit of a trend where the more you crack it, the more reduced your NOx emissions become. Because as you crack ammonia, you're forming diatomic nitrogen before it reaches the combustion zone. So you're locking in the nitrogen together, making it more difficult to form NOx. Well, I guess to a certain point, a cracking percentage where if you go too far to having fully cracked, you actually get a rise in NOx emissions again, because hydrogen has a way lower heating value than ammonia, and the temperatures of the flame will end up superseding the reduction you were initially getting, and the NOx emissions will start skyrocketing in the opposite direction again. So now we got those three out of the way, we can go to some countermeasures that apply to ammonia combustion specifically. And there are three main ones: selective catalytic reduction at SCR, selective non-catalytic reduction at NCR, two-stage combustors, and I'm gonna put a little bit of an asterisk on that one for now. Or you do a combination of two-stage combustion and selective catalytic and selective reduction. So SCR and SNCR, what these two methods do is that they exploit ammonia's ability to actually decompose NOx particles, which seems a little counterintuitive considering how ammonia is really bad about outputting it. Well, at higher temperatures where ammonia is not necessarily burning, but is still in a really hot zone, ammonia will actually react with NOx particles and break them down, and the result is diatomic nitrogen in water. So in this feature of ammonia is very practical to implement to ground-based power system or vehicles, because you can implement techniques like SCR with a porous or a honeycomb. Somebody talking right now? One second. Okay. All right. So where was I? Okay. So you can implement SCR fairly easily into ground-based power systems. And the way this works, if you look at the top diagram on the right side of the screen, you will channel your exhaust from your primary combustion process into a porous catalyst zone or a honeycomb, and you will spray in additional ammonia ahead of the catalyst. And what this catalyst does is that it reduces the activation energy of the reduction reactions. So that means you can use it means also can be a lower temperature and still get a pretty good reduction in emissions, or it increases the efficiency of the decomposition of the NOx particles. And for what I've read with SCR, you can get potentially up to 90% reduction in NOx emissions. And then SNCR, the non-catalytic version, which is the bottom one, operates in the exact same way. It just does not use a catalyst. It relies solely upon temperature and ammonia being mixed in with your exhaust. And the issue with this is that now you're having to deal completely with the activation energy of those reduction reactions. And so this method tends to be way less efficient, about 30 to 70% efficient in the reduction. All right, two-stage combustion. This is the fun part for me. So the issue with those selective reduction methods is that they may be impossible to implement effectively in jet engines. For the SCR, where you have the catalyst, it requires your flow to be slowed down and forced through a porous or honeycomb material. And you can't have that with a jet engine because you need the momentum of your exhaust flow to propel you forward. Having that blockage would severely hurt your thrust, or you might not even be able to get off the ground in the first place. And the SNCR, if you don't want to use a catalyst, but you want to try SNCR, might also not be the most optimal way to do this. Because of the speed of the flow, you got to be able to ensure you got good mixing of your ammonia reducing agent in the exhaust flow. But the speed of the exhaust is too much, and there won't be enough time for those reduction reactions to happen. So instead, what I've read in a few papers, and you can see in the top right diagram, is you can use two-stage combustion. And what the point of this is that you can have a non-catalytic reduction effect within the combustor itself before the exhaust leaves that chamber. And the way it works is that in the primary zone, which is the front half of the combustor where your main fuel and air enter, you will inject an equivalence ratio of 1.1. That's the optimal that's been found. The equivalence ratio of 1.1 of ammonia, of your ammonia fuel in your air. And what this does is that it will fully deplete your oxygen, hopefully, because the oxygen will prioritize the combustion reaction with the ammonia. And as a consequence, you get lower NOx generation. And with the zone being fuel rich, you have fuel particles left over that didn't get burned. And with it being ammonia in a hot zone, the ammonia that's still whole will break down into hydrogen or nitrogen, or the different radicals that are like NH, NH2. Those are free to move to the secondary zone. In the secondary zone, that super hot exhaust comes in, you will bring in secondary air to fulfill a global lean equivalence ratio, which is where all your fuel gets used up, but you still have a little bit of oxygen left over. And with this combination, what you should have is something called thermal denox, where those radicals from the primary zone being in this hot secondary zone will further reduce the NOx emissions from the secondary zone. So you should have a net drop in NOx emissions from the midpoint of your combustor to the outlet. And in that red box I'm showing right here, this paper showed a CFD study that they did using large eddy simulations in ANSYS. Actually, I believe this was OpenFOAM. I don't remember which one it was. But you can see where if they increase both the overall lean equivalence ratio and the primary zone equivalence ratio, there's a trend that shows that the overall NOx drops. But then if you go outside that red box to the far right, you have the situation where now you have too much fuel in your primary zone that's going to burn hot in the secondary zone, and now you get an increase in NOx emissions at the outlet instead of a drop. And the sweet spot, for what I can tell from a couple of the papers, is that you want a primary zone equivalence ratio of 1.1. And then the secondary is a little bit more finicky. And I haven't really found a straight answer on that, but one of the papers showed based on this diagram that a lean equivalence ratio of 0.35 is the other parameters you need to achieve optimal reduction. And this is where my work comes in. My job on the NASA Clean project is to assess and address the NOx emissions from the engine we are designing. And so my work focused a lot on combustion modeling. And for the Boeing 737, the base engine is the LEAP-1B. And those engines use the TAP2 angular combustor from General Electric. And the reason why I use annular combustors is because those have the most uniform temperature profile along the outlet ring of the combustor, and they're pretty fuel efficient. So to match the performance of the LEAP 1B, we need to keep as one-to-one with them as possible. So I am currently learning how to design annular combustors, and right now I am trying to validate the trend of NOx reduction with two-stage combustors. So that once I validate it, I can move forward to fully designing a combustor for our engine. And what this will allow me to do is that it will allow us to generate a map of NOx emissions over the course of our flight profile, because the EPA has regulations on your NOx emissions, and we need to see if we meet those criteria, because if not, you can't get that stamp of approval if this ever were to go to market. And then another little side note is that using that combustor, we'll also investigate the effect of cracking the ammonia to verify the trends in NOx emissions with that cracking percentage. And you see at the bottom of the screen, these are older simulations that I've done when I was first learning how to do annular combustors and in ANSYS Fluent. And this is very rough geometry. It's back when I had my math wrong, so the combustor turned out a little bit stumpier than what I intended it to be. And now this is where we get into my struggles. So far, I have currently been unsuccessful in recreating the NOx reduction trends of a two-stage combustor. If you look on the right side of the screen, at the top is a NOx parts per million contour that I made myself in ANSYS Fluent. And some important notes about the combustion modeling techniques I was using is that, number one, the mechanism that I was using, I downloaded off the website of the correct modeling group. The mechanism is called NH3. And it should be a good mechanism because it was developed within the past few years, so it should have some fairly up-to-date ammonia kinetics going on. And in the exact combustion model that I use, it's something called the flammable generated manifold model. And with this method, instead of calculating all the finite rate kinetics in real time, it pre-calculates all the kinetics based on different inlet conditions for the fuel and oxidizer and the equilibrium pressure of your simulation. And it pre-tabulates the chemistry into lookup tables that are parametrized by the mixture fraction of fuel and ammonia, of fuel and oxidizer, and also the progress variable, which is a measure of the extent of the reaction. And what this does is that you get a fairly detailed combustion simulation in a really small amount of time, compared to if you were to do the finite rate chemistry method, where every single species is tracked individually by the program. The one main drawback to the flammable generated method, to the FGM model, is that it may miss some of the nuances with chemistry. I've actually been in contact, I was able to contact the author of the paper that made the contours of the two-stage combustor last night, and asking about the flammable generated manifold model, if that should theoretically be good enough to get accurate readings of NOx emissions. And he said no. So that means that I need to use the finite rate chemistry models. The problem, this is where my major roadblock is that ammonia mechanism that I downloaded from the correct modeling group website has some kind of formatting issue or defect in it that's preventing me from loading it into the finite rate chemistry models. And I don't know, is it something wrong that I've done on my end, or if there's some bug in the program that's preventing me from using it. But with the formatting issues that ANSYS is throwing me, it's calling into question the accuracy of those FGM simulations that I did that gave me my contour above. And this is a massive headache, because without live testing, the only real way you can get a read on the emissions from your power system is to do CFD analysis. And live testing is expensive and complicated. You need the right equipment. You need a big test facility, which is something that for now we can't really do with the clean project, at least not for the time being. So I need a detailed chemical mechanism, not just for ammonia, but for any fuel that you want to try, and it has to be good and up to date and accurate. So right now, for me, the only place I've been able to find an actual detailed source of mechanisms is that correct modeling group website. The problem is that more often than not, many of those mechanisms do not work in ANSYS Fluent for whatever reason, whether it be there's some formatting issue on line 10,000 out of like 50,000, because a lot of hydrocarbon mechanisms could be thousands of species long. Or even with the ammonia, I remember there being some issue with the thermodynamic polynomials, but they seem to be in a good format based on what I've read up on the syntax of kick-in mechanisms. So I'm stuck on this front. But what I've found within the past couple of weeks is that there's another mechanism called the C3 MECV 3.5. And you can download this for free from the website of the Computational Chemistry Consortium. And what this mechanism is it's a consolidation of a bunch of different hydrocarbon reaction networks, and they bring them all into one mechanism. And they've made this version, the 3.5 version, I think within the past year or two. And this thing was made by a collection of research groups shown in like that bullet point down towards the bottom. And the issue with this mechanism is that because of its size, I cannot import it into ANSYS Fluent. And whenever I try to load it in, it threw me an error saying I'm only allowed 700 species. This mechanism has 3,761, ammonia included. And because ANSYS does have chemistry reduction methods built into it that makes the calculation easier. So I can ignore the other carbon-based fuels and species and just focus solely on nitrogen, hydrogen-based stuff. But I had to be able to load it in first. But this mechanism was actually made especially for the program Converge CFD, which is a competitor of ANSYS. And Converge CFD, from what I understand, is built more for combustion simulations than ANSYS is. So here at Tennessee Tech, we've been looking into getting the software installed so I can try this mechanism, because the academic license is free. And so until then, my request to the audience listening in is that if you guys have any information or any guidance on where to point me, so I don't have to wait on Converge CFD to be verified by campus, and I can keep moving forward, it would be greatly appreciated, because right now I'm at a bit of a roadblock. And before I close out, I want to give a special thanks to Dr. Matthias Ime from over at Stanford University. Over the past month or so, I've gone back and forth talking to him over Microsoft Teams and Zoom for help with combustion modeling. And the information he's given me has been really valuable. I just wanted to shout him out. And I want to thank the NASA Clean Project for funding the project, and me and the friends I've made working on this thing. And we do a lot of good work. It has been quite an experience. And thank you.